Namaskar. You're watching CEC Gurukul Live. I'm Monad Lakha from the Department of Computer Science, Aryabhat College, University of Delhi. Today I will be taking the lecture on Introduction to Operating System and Processes. What we'll be discussing is, we'll be defining what operating systems are and its goals. We'll be briefly discussing the operating system organization, operations and services. And we will have some overview of some operating system developments like multiprogramming, time-sharing and real-time systems. We will then discuss operating system processes and process states. Now, what is an operating system? An operating system is an interface between a computer user and the computer hardware. It controls the execution of various programs. The OS controls and coordinates the use of hardware among various applications and users. It is a software that manages the computer hardware. The purpose of an operating system is to provide an environment to the user so that the programs are executed in an effective and convenient environment. The operating system is the one program running at all times on the computer. This is usually called the kernel. So the whole operating system or the whole software of the operating system cannot always be residing in the memory. It is only the kernel which is residing in the memory, and that would be running at all times. Now, what are the other software that would be residing in the memory? You could have either the system programs which are associated with the operating system and ship with it, like linkers and loaders and compilers, or you could have application programs like Microsoft Office, which are running along with the operating system. The examples of the operating systems that we use in today's time or that we commonly use are Apple iOS, Microsoft Windows, Google's Android OS, Linux and Ubuntu. The components of computer system, if we see the abstract view, what we have is, we have at the lowest level is the computer hardware, and above that is the operating system, and which lies between the hardware and the system software and application programs. In your application programs, you will have compilers, linkers, loaders, text editor, database programs, and then you have users which are using the system programs and application programs. So as you can see in this particular figure, the operating system is required and is essentially the interface which is mandatory to have on your system so that your user can get some work done out of your system. So you have your hardware which provides the basic computing resources, and part of your system you have the CPU, which is the central processing unit, as your processor, your RAM, which is your random access memory. It is also called the primary memory or the main memory, and your IO devices. Then you have the operating system, which controls and coordinates the use of all the hardware amongst the application and the users. You have the system programs, which are the programs associated with the operating systems and are shipped with it. Examples of your system program are compilers, assemblers, text editors and device drivers. Application programs define the way in which the system resources are used to solve a computing problem. For example, word processors, web browsers, database system, your video games are all examples of application programs. And lastly, the users. The users may not necessarily be just people, they could be machines or other computers. Now, what does an operating system do? So, the functions of an operating system can be broadly categorized as: 1. A resource allocator. The operating system manages all the resources of the system, whether it is the CPU, the memory, the printers or the disk or any other IO device. The operating system services the request for these resources so that the system is used in an efficient manner. It is also a control program. The OS controls the execution of programs. It ensures that the computer is used properly and prevents errors from occurring. The functions of the OS depends on whether we are considering the user perspective or the system perspective. Now, what this essentially means is that what will a system do, what will a computer do, depends on where we are going to be using it. And from a user perspective, a user will always want that the computer or the system should be convenient to use and it should have a good performance. In mainframe and mini computers, these are shared computers. You need to satisfy the requests of all the users, so such systems are designed in such a way so that it meets the requirements of multiple users who are sharing the resources. Workstations, in these systems, the users have dedicated resources. They are also frequently use some shared server resources. Handheld computers, just like our smartphones and tablets, these are systems that have limited resources and battery life, so they are optimized for usability and battery life. So the way the functionality that these systems would have would be limited, or depending on the size of the memory as well as the battery life. Embedded computers that we can see in our microwaves or washing machines or more such systems, these computers have little or no user interface. So this is the functionality, or this is what these specific computers do. Now, what are the goals of the operating system? Now, depending on, as we had just discussed, depending on what would be the functionality of that system, that would govern what the goals are. So the first thing that you need to decide is what is the functionality of the operating system, and hence decide what are the goals. So the OS goals are defined before the design of an operating system begins. These are based on the way the system is going to be used. The hardware is designed or chosen based on the operating system goals. So obviously the hardware will differ, whether it is your handheld computer or maybe your embedded system. A microwave, the interface that you have for a microwave is very different from what you have in a tablet. So the hardware is also different because the goals of the operating system are different. Now the basic goals that is common to all the particular types of systems that we have are that the operating system needs to execute programs and solve user problems easily. It should be able to, it is built in such a way that it permits the effective development, testing and installation of new system functions without interfering with services already available. Now it goes with any particular software that is being developed, that a software, there may be errors in it, or more importantly, you may be coming out with different versions of the software which have more functionality. Now the previous version should be easy to change, it should be easy to test, and it should be easy to install so that new versions can work on the older version. Secondly, the computer system has to be convenient and to use, and it has to be suitable for whatever purpose it has been designed for. And you use the computer hardware resources in an efficient manner and in an easy way in which they can be used by the user. Now in computer system organization, if you see a modern computer system, as we have just discussing, that you have the CPU, you also have a memory, and all of these are connected to other devices as well. Your devices could be your disk, your mouse, keyboard, printer, or your monitor, which is your display. Now all of these are connected through your bus, which is your system bus. Now every device has to have a device controller which is specific to that particular device. It will also have a buffer which will store the information that has to be communicated between the computer and that particular device. So a general purpose computer consists of processors. One or more processors can be there to carry out your processing functions. If you have one processor, it is called the central processing unit, and you can also have more than one processor. That is a multiprocessor environment. You have your main memory, which is also your primary memory. This stores the data and programs within it. So any program which needs to execute has to be in the main memory. Now the important part of the main memory or the primary memory, that it is a volatile memory. It is the random access memory or RAM. So when the computer is shut down, the contents of the memory are lost. You also have I/O modules. We were just seeing that there are various I/O devices which are connected to this system. So these are required. So when you move the data within the computer to the peripheral devices, these peripheral devices are basically your external environment, and these can include your secondary memory like your pen drives, your CD or your flash drives, or your communication equipment like your LAN cables, or it can be your terminals. Each device is connected to the common system bus through a device controller. We had just seen that in the figure. Thus, each device controller is responsible for the specific device it is connected to. Example, there will be controller for a mouse, corresponding one for a keyboard, a printer, a monitor, and disk drivers. Now, why is this device controller actually required? The way the computer stores information, it only stores information in zeros and one. Now, all the devices may not be getting input from the user in terms of zeros and one, and they are also may not be displaying the output in zeros and one. For example, in mouse, we do a mouse click, we do a press the mouse button and also drag the button. So that those kind of information has to be converted into a form which is understood by the computer, and that is done by the corresponding device controller of the mouse. Then we have the system bus. The system bus provides communication between the processors, the main memory, and the I/O modules. Now, what we were talking about so far was the hardware, whatever hardware, and what was the function or brief function we had discussed for each hardware that is there in a computer system. Now, this hardware is of no use unless we use it through a program. And what will run the particular hardware, or what will use the particular hardware? It is the operating system. So the operating system actually resides in the disk. So it needs to be available to the hardware so that the processor can start executing it. So a special program is designed. It is called the bootstrap loader or the bootstrap program, and it is designed for this purpose so that it can bring the operating system in the memory. Remember that the memory is a volatile memory. So when you had shut down the system, the operating system that was residing there has been erased. It is because it was in the volatile memory. So it is residing in the disk. It has to be brought into the main memory. Now, initially when the power is switched on, you do not know what program to run, and that program first has to be brought into the main memory. So what you use? We use another type of memory, which is your random only memory, or we can also use its variant, which is EEPROM, which is electrically erasable programmable read only memory. So the bootstrap loader is a small piece of code that is stored in your ROM. This is a firmware. Why is it called a firmware? Because it has a small program stored within it, and this program is basically stored in the ROM when that ROM is fabricated. That's why it is called firmware. So when we power on the system, the processor starts executing the bootstrap loader, which resides in the ROM. The job of the bootstrap loader is to locate the kernel, load it into the memory, and starts its execution, because the kernel, as we had discussed, is the core part of the operating system. It is also responsible for initializing all aspects of the system, like the CPU registers, device controllers, and memory contents. So once the kernel is loaded, the system is set to be running. Now sometimes the bootstrap program may not be too simple. So there's a two-step process which is used to load the kernel. In the first step, the ROM code loads the boot block at a fixed location in the main memory. And then this boot block further has instructions which will load the more complex bootstrap program from the disk. So then once the bootstrap program is loaded onto the disk, it will further load the kernel and start executing it. In the initial part of the system boot, various system elements of the computer, such as the hard drive, memory, and peripheral devices, are checked for any error or problems. If a problem is found, the boot process halts and informs the user through error messages or beeps. If no problem is found, the computer begins to activate various hardware inside the computer. So the error messages are the only way by which a user can get to know if some error has occurred during the booting process. These error messages are generally displayed on the display screen. But what happens when the error is in the display screen itself, in your graphic card? So in that case, the system also has a provision of giving beeps so that the user gets to know that the boot process has not been successful. Now there are various operations of the operating system. So once the system is booted, the operating system is ready to execute programs, and the basic operations of the operating system are as follows. So now you have the operating system and you have a program which is loaded into the memory. So the operating system has to execute the instructions of that particular program. So the CPU and the I/O devices execute concurrently. That means there are instructions which CPU is executing, and the I/O device is also doing some I/O. That means transferring some input and output to the computer. They compete for memory cycles. As we were seeing, they're using a common bus, so only one of them can transfer the information at a particular point of time. The device controller for each device has a local buffer, as we had discussed. The CPU moves data from or data to the main memory or from the device buffers. The I/O of the data is from the device to the local buffer of the controller. So what this essentially means to say is that if we have to transfer any information to the computer from an input device, from that input device it will come to the corresponding buffer in the device controller, and the CPU will pick up the information from that buffer. In the same way, if some output has to be sent to an output device, the CPU will send it to the corresponding local buffer of the controller, and then the controller will transfer it to the format in which the output device can display the information. So once the I/O is complete and their data has been moved to the controller's buffer, the controller informs the CPU by causing an interrupt. We had just discussed that the CPU and the I/O device, they work simultaneously, they work concurrently. So once the data is ready in the buffer, then the I/O controller informs the CPU through an interrupt that yes, the data is ready in the buffer, it can now be transferred. One very important aspect of or function of an operating system is interrupt handling. Now there are various types of interrupts. To handle each type of interrupt, the operating system obviously has a separate segment of code that determines what action needs to be taken specific to that particular interrupt. This is that is, each type of interrupt is implemented differently. So when you have an interrupt, what happens corresponding to all of them? An interrupt transfers to control to an interrupt service through the interrupt vector. The interrupt vector contains the address of all the service routines. The interrupt architecture must save the address of the interrupted instruction. For this, the operating system preserves the state of the CPU by storing registers and program counters in the PCB or the process control block, which we will see subsequently. So the interrupt, whenever it is called, and there can be multiple types of interrupts, that a particular device 1 has given an interrupt that the data is ready. It could be a device 2 that there is an interrupt that another data from another device is ready in the buffer. So but each of them have to be handled differently. So how do we know? So it's just like you have an index. That interrupt vector is like an index. So the particular interrupt, the type of interrupt, it will index into the index vector. From there, the corresponding address for which will correspond to the code corresponding to the interrupt to service the interrupt would be there, and that would be executed. A trap or an exception is a software generated interrupt. It is caused either by an error or a user request. So this is another type of interrupt. So basically your operating system is interrupt driven. So operating system would continue to do its particular task unless it is requested to do otherwise. That means an interrupt, it receives an interrupt, so then it services that interrupt. Now very briefly, when we study the computer system organization, we also have to study the storage hierarchy. Now why is this important? As we can see in this particular figure, we have a pyramid-like structure. Now this structure basically means that the memories which are higher up in your hierarchy, these memories, as you can see, the size is smaller, so that means the amount of data they store is smaller, and those in the lower parts of the pyramid, they will store larger amounts of data. Now how do you distinguish, or why do you even have this particular pyramid? Now you know that the central processing unit or CPU executes instructions in a fast way. So that means the speed at which it executes instructions is also needs to be provided those instructions at that particular speed. At top of the hierarchy are the registers. So they basically work at the same speed as the CPU or the processor, because they are fabricated on the same chip. Now usually we were talking about the fact that your program and data has to be in the memory or the main memory for it to be executing. But the speed at which the CPU can access this information from the main memory, it is slow. So the CPU actually keeps on waiting till the time that the data from the main memory is available in the registers. So what happens is you have interleave another memory, which is a faster memory, a cache, which is between a faster registers and a slower main memory. These are generally on-chip memories that are there. Cache is generally on-chip. You could also have a cache which is off-chip, meaning to say on-chip cache means that it would be also be fabricated along with the chip which has the processor and your registers. So any data which now the CPU requires, it will first look for it in the cache. If it is available from the cache, which is a faster memory, obviously it will get it as a quicker time, and otherwise it will then fetch it from the main memory. Below the main memory are your magnetic disks, and then your optical disks and your magnetic tapes. Now this hierarchy also signifies another aspect. As you go up in the hierarchy, as I just mentioned, that the size or the capacity of that storage is less. So that means the amount of data stored per unit area is less or the capacity of that memory of registers. You usually have just a few bytes of registers. And the second thing is the speed is, which I also mentioned earlier, was the speed of the various memories which are higher in the pyramid. Like for example, the register, the speed of access from a register is much faster than from a cache, which is faster than your main memory, which is faster from your disk, and so on. And the third aspect is, what is the cost per bit? The cost per bit of the memory which is at a higher in the pyramid would always be, it is more expensive to fabricate such a memory, so that cost per bit is higher. So as you go up towards the higher memories in your pyramid, what will happen is your cost per bit will increase, the speed of access would also increase, but the amount of data which is stored on that particular memory will decrease. So the concept of caching can be used in a lot of areas when we are talking about in computer systems, and this is whenever you have some data has to be stored at a place which is can be accessed at a faster speed, then we use the cache. And all these particular memories, they are basically distinguished from each other also in the way they are fabricated, the technology used to fabricate it and to store the data. Now the operating system provides a lot of services. Some of these services are those which directly a user like you and I use. So the operating system provides an environment for execution of programs and services. So a set of operating system services provide functions that are helpful to the user. For example, a user interface. We generally like to use a system which has a good user interface, and a user interface could be a command line interface, but more popular ones that we are used to are graphical user interface that we use in Windows, which has become very popular, and then touchscreen has a specific type of interface. Another important aspect I as a user would require is program execution. So there should be a mechanism by which the users can execute programs, and the system should be able to load the program into the memory, run the program, end its execution, and in case there are errors, it should be able to inform the user that certain error has occurred. Obviously, any particular program which needs to run, they need to have certain I/O operations. So an OS service is required for running program which requires I/O or may involve a file or an I/O device. So when we are talking about input output, it could also be from a file, it could be from a device also. File system management is also required, so servicing for reading, writing, creating, deleting, searching files and directory is also required. Communications processes may exchange information on the same computer or between computers over a network which requires services. So that means different processes, which are basically your programs and execution, need to communicate with each other. Those services need to be provided by the operating system. And error detection, operating system should be able to detect possible errors and appropriately inform the user. So just like services for the user, there are a lot of services which the operating system provides, which are also essential for the running of the computer system. So one important one is your resource allocation. So resources must be effectively allocated to each of the users or the multiple jobs which are running concurrently. These could be your CPU cycles, your main memory, your file storage, and I/O devices. You need to have certain accounting services which are required to keep track of various resources which a particular user uses, like we were talking about the resources, how much time they used and how effectively they use the particular resources. Protection and security of concurrent processes also is very important. You do not want one particular process to interfere with any other process which is running concurrently. Protection ensures that all access to system resources is controlled. Security of the system defends external I/O devices from invalid attempts to access the system. Now, there are certain system developments which are important and significant in the whole life cycle of the development of an operating system. So, earlier systems had only one particular program residing in the memory. It was also called a uniprogramming environment. Now, since the I/O devices were slower than the processor was often left idle. The single program obviously could not keep the processor and the I/O devices busy at all times, and there was underutilization of resources. So this led to the development of multiprogramming. Multiprogramming allows multiple programs to reside in the memory. When one program was completing the I/O, the processor could execute another program that was residing in the memory. This increased the average resource utilization and throughput, and the multiprogramming made batch processing more efficient. Now, this particular diagram basically shows how in a multiprogramming environment, apart from the operating system, you have multiple programs, or in this case they are called jobs and programs, and even processes, as we will see later. They are used synonyms in various texts to signify the same thing. So in your main memory you have your operating system and multiple programs or jobs are residing there. The next is your time sharing systems. These are sometimes you have jobs which require you to interact with the computer. The user needs to do a lot of interaction, and what this essentially means is that in an interactive environment, for example, if we go to withdraw money from an ATM, it is an interactive application in which you are prompted to maybe give your PIN. Then you give some information, then it waits for you, it does some processing, then it waits for you to give some other information. So what does it mean? That it is also the speed at which you finally execute the application is also governed by the speed at which the user is giving the response. So the time sharing, this is an example of a time sharing environment. So time sharing is a specialized case of a multiprogramming environment. So a multiprogramming environment in which the processor handles multiple interactive jobs is a time sharing system. In this, the processor time is shared among the multiple users who simultaneously access the system through terminals. The OS interleaves the execution of each user program in short bursts or short quantums of computation. So how is that short computation? Because I have given some input to the program will then do some processing, then it will prompt me for some other information, and then I will also give some information, it will do the processing. So this small bursts of processing is the small quantum of computation that the program is doing and the CPU is doing on behalf for the program. So due to the comparatively slow human reaction time, the response time for time sharing is similar to that of a dedicated computer. I as a user will not get to know there are multiple users using the same system, because my particular program is just working at the speed at which I am working. So as an example, If a user requires 2 seconds of processing time in a whole minute, that means the amount of time that the processor needs to execute the instructions for user 1 is just 2 seconds. So what will we do with the 58 seconds? So we can also have other programs running simultaneously, other user programs running, and on an average you can have about 30 users working on the same system with almost the same response time. So we have increased the efficiency of the system by using by making the system as a time sharing environment. The next are your real-time systems. Now, multiple users again simultaneously may request queries or update the database. Now, real-time systems are dedicated systems that need to strictly adhere to some defined constraints. These are called hard real-time systems, like industrial control or robotics. Like in a chemical industry, sometimes you have a mechanized plant in which everything is controlled by the machine. So it has to be very accurate. The time is very important. Even robotics, when your robotics surgery is being done, then also it is very critical because it is life threatening if the time guidelines or the accuracy is not met. In soft real-time systems, the defined deadlines are desirable, but they are not mandatory. These examples of such systems are limited utility, industrial control and robotics, or you have video conferencing or virtual reality. Now, we were also talking about the fact that we have the user and program, and you have the operating system there. Now, we also were talking about protection, protecting one program from harming the execution of the other program, especially the operating system. So since your user program and the operating system reside in the memory simultaneously, it becomes all the more important to have this protection in place. You have to protect any user program from accessing the memory location which is there allocated to another user program or the operating system. So for the purpose of execution of the system, a mechanism to distinguish the execution of a user program and the execution of an operating system is required. So hardware support was developed to make this distinction. You have your dual mode operations allow the OS to protect itself and other system components from malicious user programs. Two modes are defined, the user mode and the kernel mode. So the hardware protection is achieved by using a mode bit. So through this bit, the user can decide when to run the user code, and in that case the mode bit is 1, and when if it is any particular instruction is running in the kernel mode, the mode has to be switched to a bit 0. The mode bit has to be made to 0. So some machine instructions, when executed by malicious users, say through a malicious program, that means a virus for example, can harm the system. These critical instructions are designated as privileged instructions. So those instructions, OS instructions which are very critical, they are taken as privileged instructions. So privileged instructions can be executed only in the kernel mode. So when a user program has to specifically explicitly call the privileged instruction, obviously for all operations the user program needs to call privileged instructions, and they can do it only through your system calls. So the system call will always execute your privileged instruction. So a system call changes the mode to the kernel mode, and after completion it returns to the user mode, and before that it converts or changes the mode bit back to 1. So as you can see here in this particular diagram, we have the user mode and the kernel mode. You have a user process running, and this calls a system call. We just said that to run any privileged instruction, even if I have to write something onto the terminal, I have to call a system call. So the user program in this case calls a system call. So there will be a trap. It will go to the kernel. The kernel will then change the mode bit. In the user process, it was in the user mode bit was 1. So when it comes to the kernel, the mode bit would change to 0. The particular system call is executed, and after the system call is executed, the mode bit is changed to 1 and the control goes back to the user program. So system calls are programming interface to the operating system services. These execute the privileged instructions and are usually written in high-level languages like C and C++. They can be accessed through user programs in 2 methods. First is by calling a system call. As we had just seen, you can just call directly a system call, and you can directly through your program, and the other is calling a high level application programming interface, a function from a API or a high level application programming interface. Now the common APIs that are used are the Win32 API for Windows, POSIX API for POSIX based systems like Unix, all flavors of Unix, Linux and Mac OS X, the Java API for the Java virtual machine. So how are these implemented? The system calls, typically just like we have in interrupts, we had in the specific interrupt is handled by a specific function, and you have an interrupt vector. It is the control goes to the interrupt vector to see the address of the system call. In the same way, when a system call is implemented, because there are different privilege instructions corresponding to every privilege instruction, you have a specific system call. Every system call is given a number, and the system call interface maintains a table from which you can index. From the number of the system call, you can get to know what is the address or where the code corresponding to the system call resides, just like in interrupts. So the system call interface invokes the intended system call in the OS kernel. It then returns the status of the system call and any other return value. So obviously when a particular system call is executed, there may be some return value that is also there. So the caller program does not need to know the details of the system call implementation. So that is the whole idea, especially when you are using APIs. If user program calls an API, it passes the required parameters, and the user uses the results that the system call has returned to the API, and then hence the API has returned to the user program. So most details of the OS interface are hidden from the programming by the API. Now in this particular figure, as you can see, the user program is directly using the first method of directly calling the open system call. It is working in the user mode, and then the system call interface, through the system call interface, it enters the kernel mode bit is changed to 0. It indexes into the system call table based on the system call number, say I. It then gets to know where is the code corresponding to this open system call. That particular code is the implementation of the code, the control goes to there, that particular code is executed, and then the return goes back to the user program. Another method is that we call a system call through using an application programming interface. Now for example, you have a simple C program in which I use a printf statement. Now we know that printf is in the stdio.h library, so the implementation corresponding to printf would be there. That's why we include that particular file. Now the user program, all the user program needs to do is just write the printf statement. Now this printf statement is part of your standard C library, and this printf statement will internally call whatever is your write command. When you are printing, you want to print to the terminal, so it will be a write system call, and the corresponding write system call is executed in the kernel mode, and again it is passed back to the user again through the standard C library. It is passed back to the user program. Now we have talked about programs, and we have also talked about the fact that the programs also reside in the memory with the particular operating system, and then we talked about multiprogramming and time sharing and real timing systems. Now when these particular systems were developed, they made things a little more complicated. There were certain problems in the timing and the synchronization. Because there were multiple programs that were running, the processor had to switch between the various programs in the main memory. Once one particular program was running, say program 1 was running, it went in for IO, then the CPU does not have to stay idle, so the processor started executing the second program, but you had to save the whatever was the state of the program 1, so that it can resume from that particular point. In the same way, in time sharing, the response to the you had to respond to the needs of the various multiple users, and obviously with a decent response time, which is same as what a user gets when you are using a dedicated system. Real time systems, obviously the response time has to be strictly adhered to. The time constraints are very well defined in this particular case. So interrupts obviously would stop the execution of one particular program, and the processor would start executing another program. The partially executed program has to be resumed from where it had stopped. So the state of that particular program has to also be saved somewhere. Okay, so every context switch requires the program specific information of the partially executed program to be saved. Now context switch basically means that one particular program is stopped, program 1 is stopped, whatever were the values of the current state of that particular process, that is saved, the register values are saved, and the process 2 program 2 starts executing. So whatever was the last state of the process 2, that has to be brought into the memory, because the processor has to start executing it. So this is called a context switch. So this led to the development of the concept of operating system processes. So each execution of a program created a process which had information regarding the details of the process, and this was stored in the process control block or the PCB. So what this basically means to say is, just like what we are talking about, that the context switch basically it needs to save the state of a particular program. So where will that state be saved? You need some data structure, and that data structure has to be assigned to some entity. So that entity is your process. So your processes are central to the design of an operating system. So what is a process? It can be defined as any one of them. So it is the central to the design of operating system. It can be defined as an instance of a running program. So I can have a program and I can have various instances of that particular program. So each instance of that program will be called a process. A process is also called a program in execution. It is an entity that can be assigned to a processor and it can be executed by the processor. The program is a passive entity which is stored in your disk. So what you store in your disk is basically your executable file, and your process is an active entity. So once a program comes into the memory, it is loaded into the memory, it becomes a process. So that executable file, once it is loaded into the memory, the program becomes the active state. It is called the process. So a process obviously needs resources to accomplish a task. It needs the CPU, the memory, the IO, the files, and the initialization data. The process termination requires these reusable resources to obviously be reclaimed. You cannot have resources endlessly being given out to processes. They need to be reclaimed because you have limited resources in the system. Typically systems have many processes. You have user processes and operating system processes which are concurrently running. You can have one CPU running it, or we can have multiple processors which are running it. So a program can be executed or started in a couple of ways. Either you can have, like we had discussed earlier also, you can have a GUI mouse click or execute, which will click a name of an executable file, or it will click a icon, or on a touch screen you would just tap on the particular icon which is there on your touch screen. Or you could also use a command line interface and type the corresponding command which will execute that program. So that will initiate the execution of the program and will create the process. So every program can have several processes. Now we had initially discussed how in a memory you can have the operating system and you can have various jobs or processes in the memory. Now this particular figure basically shows how what does one particular process looks like. What does information or data does it store? So any process has multiple parts. You have a program code. It is also called the text section. Then you have the current activity, which is your program counter, value of other registers, process registers, that is also stored here. You have the stack, which contains the temporary data and any functional parameters or some return values that are stored here. You have a data section which contains the global variables that this process uses. You have heap containing memory which is dynamically allocated during the run of that particular process. So corresponding to every process, you will have a process control block. It is a data structure which has all the information associated with the process, and it is created whenever a new process is created. This is stored in the memory. This data structure is called the process control block or the PCB. It is also called the task control block. Now, what information does the PCB store? First of all, it stores the state of the process. The process can be either in the running state or in the waiting state. We will just subsequently see what are the different states of a particular process. Then it also stores the program counter. Program counter is the location of the next instruction that has to be fetched for this particular process. So, the program counter, the value is stored. The value of the CPU registers, the contents of all process registers will contain information of the partially executed processes, as we were just discussing. When a process the CPU was executing, say process 1, when that stops executing, whatever was the process state, the program counter, register values, that basically is stored in the PCB corresponding to that particular process. The CPU scheduling information is also required. Priorities are set which are required for shareable resources, and scheduling queues and pointers are also specified. Now, sometimes we have resources like say printers which are used by multiple processes. Now, if it is not a shareable resource, then in that case you can have only one processor using it at a time. So, the various resources are assigned according to the priority. Even when to have to schedule the operating, CPU scheduling has to be done. That means it has to be decided which process will get the CPU. The CPU will run with the which process. Then also sometimes an algorithm can be used, a mechanism can be used which uses priority. Then memory management information is also required. It basically stores the information of the memory allocated to a particular process. Accounting information is required. The amount of CPUs, the clock time elapsed since the start of execution, what are the time limits of maybe using a particular device, all that accounting information is maintained in the central processing unit. The I/O status information is also required, and so this is stored in the PCB. What are the devices allocated to the process? What are the list of open files? All this is also saved in the process control block. This is just an example of just to showcase what a process control block saves. Process state, then you have a process number. Now, every process that is created, a system generated unique number, which is the process number, is created. You have your program counter, you have your other CPU registers, what are the memory limits, meaning to say what are the allocated memory, list of open files and other information. This is what is stored in your process control block. The next is your process states. Now, a process, we know that even if I have multiple processes in the memory, but every process cannot be executing. I have only one CPU, the CPU can execute only one particular process at a time. So, the other processes will not be in the running state, they may have some other state. So, during the lifetime of a particular process, it goes through various stages. So, as a process executes, it changes states a number of times. These states are new. So, when a process is created, it is admitted to a system, it is in the new state. This is when the corresponding PCB is also allocated to the particular process. Then, when the processor is assigned to that particular process, then that process is set to be in the running state. That means the instructions of that process are being executed by the CPU. We also have the waiting state. Now, sometimes the a process is waiting for some particular I/O to occur, or it is waiting for some event to occur. So, in that case, the process would be in the waiting state. Once the process goes out of the waiting state, that event has occurred or that particular I/O has occurred, it is now ready for to be executed. So, it will come in the ready state. It will wait till the processor is allocated to this particular process. And one more state is your terminated state. Now, the process has finished execution, it can exit the system, it can be a normal exit or it can be an abnormal termination. So, in that case, it would be in the terminated state. Now, there are many other more detailed states, and depends on the operating system, you also could have a block state. Now just seeing the process state diagram in this, what we see is you have a process which is admitted to the system. The new process will get a process control block, and it will be once it is admitted into the system, it will go in the ready state. So there will be a queue of all the processes which are in the ready state, which are ready to execute. Now the particular CPU scheduling algorithm, whatever is defined for that particular operating system, that will decide which process out from the ready queue would be picked up for the processor to execute. So the scheduler dispatcher actually decides which particular process amongst the many processes in the ready state which are in the ready queue would be allocated the processor. So once it is allocated to the processor, the process is said to be in the running state. Now it will keep on remaining in the running state when either three type of events occur. One, that the process has the program is completing, that there are no more instructions to execute, it has to terminate, it will exit the system. Even when certain errors have also occurred, in that case also it will terminate with some error message, so that also will lead to the process termination. You could also have an interrupt. For example, the processor may be assigned to the process for a specific period of time. So in that case, if there is a timer interrupt, so then the process can no longer execute, and the process will now have to go into the ready queue. It will be in the ready state. Another way by which the process will stop running is that, for example, the process is going in for an IO. You gave a print statement, so it is waiting for some IO to complete, only then the control can come back to the process. So when a process has to wait for some IO or some event, the process goes in the waiting state, and when this particular event occurs or this IO is complete, then it goes back into the ready state. And again, this particular process goes on until your particular process either terminates in a normal fashion, that means its instructions have completed, or it terminates abnormally due to some error. So basically we discuss what an operating system is, what its goals are, computer system organization and operations, hardware protection and system calls were also discussed, computer system services which are useful from a user perspective as well as a system perspective were discussed. An overview of a few computer system developments like multiprogramming, time-sharing and real-time systems were discussed. Operating system processes were introduced and the process states were discussed. These the references used are operating system concepts by Silbersetz, Galvin and Ganey, and operating systems internals and designs and principles by William Stallings. Thank you.